What need to say for science? QR, or quick response codes, have become ubiquitous over the last decade. In fact, they're so commonplace that if you were to look around your room, you'd probably find one staring right back at you. Yet despite this, it isn't widely known how they work and to what extent they can be damaged and still successfully scanned. To test this, we've printed out 4 giant QR codes with different properties, and we've enlisted the help of a British favourite, a trusty can of baked beans. Before we go any further, let me take a second to explain exactly how QR codes work. There have been tons of videos made about this, which we've linked in the description below, but here's a brief overview. The first bit is fairly simple. The black and white squares on the QR code represent 1 and 0 respectively. These 1s and 0s, otherwise referred to as bits, are the building blocks of all digital information. When combined, these 1s and 0s can be used to encode alphanumeric characters such as H, 0, or 3. When you point your camera at the QR code, it will read these squares in a zigzag, starting from the bottom right. String these characters together and you can get anything from a phrase, a phone number, or a URL. However, for QR codes to work, they need to signal to the device scanning them that they are in fact a QR code. They also need to have some safeguards in place. After all, a simple picture of data can get pretty scuffed. Some of the squares on a QR code are used to store a string of alphanumeric characters, while some squares are designed to store other bits of important information, such as telling the camera or scanner the alignment, displaying the amount of error correction present, and even informing the scanner what version it is. Confusingly, version refers simply to the size of the QR code, with version 1 being the smallest and version 40 being the largest. The part we want to focus on today are the areas of QR codes designated for error correction itself, aka the backup data that allows damaged QR codes to still scan effectively. This is referred to as redundancy. QR codes come with different levels of redundancy from low to high, with high redundancy allowing for greater damage than low redundancy QR codes before they are unable to be scanned. There are 4 levels ranging from 7% to 30% of data which can be damaged and have the QR code still work. Now for us at Kakapo Labs, this part is particularly important. One of our brands, Pink Penguin, uses QR codes to protect valuables. This enables anyone who comes across a lost item with a Pink Penguin tag or sticker to scan the QR code, which will display the relevant information, giving the finder all the information they need to return the item. Of course, whilst our stickers needed to be small, and therefore low version, they will be sitting in pockets or attached to bags which can get battered, so we gave them a relatively high level of redundancy. Whilst this reduces the amount of space available on our QR code to store data, that isn't so important for us because our landing pages have short URLs. For QR codes that are likely to only be on screen and therefore less susceptible to physical damage, a lower redundancy might be preferable so that more data can be stored in less space. To demonstrate how redundancy works, we want to see how many spoonfuls of beans it will take for our QR codes to stop scanning, and more importantly, how the different levels of redundancy affects the results. Before we start the experiment, it's important for us to check that all of the QR codes actually scan. All of our QR codes all linked to the same page, they all have the same information, there's at different redundancies. So I'm going to put 1 spoonful on each and then scan after each spoonful to see if it actually scans. Okay, that one still works. Still works. That still works. So after 1 spoon of beans, all of the QR codes still scan. 2 spoons. Still works. Still works. 3 spoons. So after the 3rd spoonful, the low redundancy QR code has stopped scanning. 4 spoons. Oh, it doesn't work. No, it doesn't work. So after 4 spoonfuls, the low redundancy, medium redundancy, and quartile redundancy QR codes have all stopped scanning. It's really interesting how the medium and quartile QR codes stop scanning after 4 spoonfuls of beans. This could be down to the splash pattern, this could be down to a number of variables. 5 spoons. Six spoons. After 6 spoonfuls of beans, our high redundancy QR code still works. 7 spoons. After 7 spoonfuls of beans, our high redundancy QR code has finally stopped scanning, so it's back to the lab. What this experiment shows is that, as with all engineering, redundancy is a trade-off. In this case, the trade-off is between the amount of data that can be stored versus its durability. The lower redundancy QR codes were able to store the same amount of data as the higher redundancy QR codes, but with less detail. This means that the lower redundancy QR codes were more vulnerable to physical damage than the higher redundancy QR codes. This resulted in the high redundancy QR code withstanding a massive amount of baked beans before it stopped scanning. But the question is, how does this error correction actually work? There are different types of error correction, but QR codes use Reed-Solomon correction, which is the same type used in CDs and DVDs. QR codes, CDs, and DVDs are all media formats which are prone to concentrated physical degradation, or, in English, scratches, scuffs, and marks. The way Reed-Solomon correction works is probably too long to explain in such a short video, but what I can say is that it uses a technique called Lagrange Interpolation. As previously learned, the data from the QR code is stored in ones and zeros, or binary, and the strings of these ones and zeros are used to generate a numeric value, even if it is later read as a letter. If we have numbers, we can do maths with them, and because we can do maths with them, we can generate equations for a line that strings between these values. In this particular case, Lagrange interpolation paired with modular arithmetic is used to generate an equation for a line which passes through all the values from a cluster of values. This allows us to do a sum to regain the values from a scanned QR code, even if they are lost. And there you have it. This is why QR codes can still scan after having a run-in with baked beans. However, just like everything else, it comes at a cost.